Section 7. Design of Cathodic Protection, CP Systems 7.1 Introduction. This section offers guidance on the development of effective and dependable CP systems. 7.2 Principal Aims of CP Systems. 7.2.1 To furnish adequate current to the structure requiring protection and distribute this current to effectively achieve the chosen CP criteria. 7.2.2 To curtail stray currents on adjacent subterranean structures, refer to Section 9. 7.2.3 To establish a system design life that corresponds with the necessary lifespan of the protected structure, or to allow for routine system refurbishment. 7.2.4 To incorporate sufficient allowance for projected alterations in current demands over time throughout the CP system's design life. 7.2.5 To position anodes, cables, test stations, and other apparatus where the likelihood of disruption or harm is minimal. 7.2.6 To provide ample monitoring provisions to assess and appraise the efficacy of the CP system's performance. 7.3 CP Design Considerations. 7.3.1 Identification of perilous conditions prevalent at the proposed installation location, and the selection and specification of materials and installation procedures that guarantee safe setup and function. 7.3.2 Specification of materials and installation methods to comply with the most recent versions of relevant codes and national, international, and AMPP standards. 7.3.3 Selection and specification of materials and installation practices that ensure reliable and cost-effective operation throughout the planned operational lifespan. 7.3.4 Selection of locations for intended installations to diminish currents or earth potential gradients that can induce adverse impacts on external underground or submerged metallic structures. 7.3.5 Collaborative inquiries to ascertain mutually agreeable solution as, for interference issues, refer to Section 9. 7.3.6 Attention must be paid to the unique conditions outlined in paragraph 6.3. 7.4 Data beneficial for CP design. 7.4 One valuable piping system specifications and data encompass the following: 7.4.1.1 Route maps, alignment sheets, etc. 7.4.1.2 Construction date. 7.4.1.3 Pipe material, fittings, and other accessories. 7.4.1.4 Line pipe and field joint exterior coatings. 7.4.1.5 Casings. 7.4.1.6 Corrosion control test stations. 7.4.1.7 Electrically isolating apparatuses. 7.4.1.8 Electrical bonds. 7.4.1.9 Grounding systems. 7.4.1.10 Aerial bridge and underwater crossings. 7.4.1.11 Plan and profile drawings. 7.4.2 Pertinent information on piping system site conditions includes the following: 7.4.2.1 Existing and planned CP systems. 7.4.2.2 Potential AC and DC interference origins, refer to Section 9. 7.4.2.3 Unique environmental circumstances such as operational temperatures, SCC susceptibility. MIC 7.4.2.4 Nearby buried metallic constructions, including location, proprietor, and corrosion control practices. 7.4.2.5 Structure accessibility. 7.4.2.6 Power availability. 7.4.2.7 Viability of electrical isolation from external structures and grounding systems. 7.4.2.8 Likelihood of lightning voltage surge consequences that might necessitate mitigation strategies. 7.4.2.9 Soil type, groundwater, geotechnical data, and land utilization. 7.4.3 Helpful data from field surveys, corrosion test results, and operational history includes the following: 7.4.3.1 Protective current prerequisites to fulfill applicable standards. 7.4.3.2 Electrical resistivity of the electrolyte. 7.4.3.3 Electrical continuity. 7.4.3.4 Electrical isolation. 7.4.3.5 External coating condition. 7.4.3.6 Cumulative leak history or inspection outcomes. 7.4.3.7 Stray DC currents. 7.4.3.8 Departure from construction specifications. 7.4.3.9 Natural pH of the surroundings. 7.4.3.10 Other upkeep and operational information. 7.4.3.11 Probability of AC interference. 7.4 For field survey work prior to the actual implementation of CP is not always mandatory if previous experience or test results are accessible to approximate current requirements, the electrical resistivity of the electrolyte, and other design elements as specified in paragraph 7.3. 7.5 Categories of CP systems. 7.5.1 Galvanic anode systems. Galvanic anodes are typically fabricated from materials such as alloys of magnesium, zinc, or aluminum. The anodes are cast, extruded, or continuously cast and hot rolled onto galvanized steel cores that sustain the alloy, to which insulated cables are typically attached. The anodes are linked to the pipe by these cables, either singly or in clusters, directly or via a test station. Galvanic anodes are restricted in current output by the anode to pipe driving voltage, the electrolyte resistivity, and the overall circuit resistance. Impressed current anode systems. Impressed current anodes are typically constructed from materials such as graphite, high silicon chromium cast iron, mixed metal oxide coated titanium, platinized niobium, conductive polymers, or steel. They are joined with an insulated cable, either individually or in groups, to the positive terminal of a DC power source, such as a transformer rectifier, solar power array, wind generator, closed cycle vapor turbine, CCVT, thermoelectric generator, fuel cells, motor generator, or DC-DC converter. The pipeline structure is connected to the negative terminal of the DC source. 7.6 Factors influencing the choice of CP system. Type factors influencing the selection of the type of CP system include the following. 7.6.1 Extent of protective current needed. 7.6.2 Electrical resistivity of the environment. 7.6.3 Location of remote earth. 7.6.4 Stray currents inducing substantial potential variations between the pipeline and earth that can prevent the utilization of galvanic anodes. 7.6. 5 Impacts of CP stray currents on neighboring structures that can restrict the use of impressed current CP systems. 7.6.6 Accessibility of electrical power. 7.6.7 Physical space accessible, proximity of external structures, easement acquisition, surface conditions, presence of streets and buildings, river crossings, and other construction and maintenance concerns. 7.6.8 Future expansion of the right-of-way zone and future additions to the pipeline network. 7.6.9 Expenses associated with installation, operation, and upkeep. 7.6.10 Environmental considerations, installation and operation. 7.7 Elements affecting CP system design. 7.7.1 Anode materials exhibit varying rates of consumption in a particular environment. For a specific current output, the anode lifespan is governed by the environment and anode material, which dictate the capacity, the anode weight, and the quantity of anodes within the CP system. Established anode performance information should be employed to compute the probable consumption rate. The design of galvanic anode systems must account for both current requirements and design life. The anode's form dictates its resistance to earth in a given environment, and, for galvanic anodes, determines their current output. For impressed current anodes, their shape and resistance govern the connection between driving voltage and current output. 7.7.2 Data on the dimensions, depth, and arrangement of the anodes and the electrolyte resistivity can be utilized to compute the resulting resistance to electrolyte of the anode system. Formulas and graphs pertaining to these factors are available in the bibliographic literature and from most anode manufacturers. 7.7.3 The design of galvanic anode systems takes into account anode to pipe potential, anode to remote earth resistance, pipe to earth resistance, electrolyte resistivity, current output, and anode lead wire resistance. 7.7 For galvanic anode performance and service life in most soils can be enhanced by utilizing specialized backfill material. Mixtures of gypsum, bentonite, and anhydrous sodium sulfate are most frequently used. The backfill is engineered to provide a consistent environment, guarantee electrolyte contact with the anode, and avert passivation. 7.7.5. For impressed current systems, the number of anodes needed can be decreased and their functional lifespan extended by employing specialized backfill around the anodes. The most prevalent materials are metallurgical-grade coke or calcined petroleum coke. 7.7.6. In the design of an extensive distributed anode or linear anode impressed current system, the voltage and current attenuation along the anode connecting header cable should be evaluated. In such instances, the design aim is to optimize anode system length, anode spacing and size, and cable size to attain efficient external corrosion control at the furthest points of the protected structure. 7.7.7. In the design of an impressed current system, the voltage and current attenuation along the structure should be taken into account. See paragraph 7.7.11, Coating Conductance. 7.7.8. When it is foreseen that the accumulation of gas produced by anodic reactions over time could hinder the capacity of the impressed current anode bed to supply the necessary current, appropriate measures shall be taken for venting the anodes. For the same current output of the system, an increase in the surface area of the specialized backfill material or an increase in the number of anodes will reduce the anode current density and may lessen gas blockage. Safety and environmental considerations should be addressed for gases released that are generated at the anode's surface. 7.7. 9. When it is projected that electro-osmotic effects over time augment the resistance of the anode bed to remote earth, then provisions shall be implemented to ensure sufficient soil moisture around the anodes is preserved. Furthermore, increasing the number of impressed current anodes or increasing the surface area of the specialized backfill materials will further diminish the electro-osmotic effects. 7.7.10. Installation locations susceptible to moisture loss, dry, arid zones, may necessitate anode watering systems or positioning anodes beneath the groundwater level. 7.7.11. Coating Conductance. 7.7.11.1. Evaluating coating quality on an existing pipeline. External electrically insulating pipeline coatings are designed to reduce CP current requirements and enhance current distribution. The quality of the coating on an existing buried or submerged pipeline can be assessed by conducting a coating conductance test, as detailed in TM0102. The outcomes of this test, expressed in MSM2, MSFT2, and normalized for 1000 OCM soil, can be compared to the values presented in Table 1 for estimating coating quality based on electrical parameters. Table 1. Estimating coating quality based on electrical parameters. Coating quality, normalized specific coating conductance, microsiemens FT2, microsiemens MM2, excellent, 10, 100, good, 10 to 50, 101 to 500, fair, 51 to 200, 501 to 2000, poor, 200, 2000, estimating percentage bare. The typical protective coatings employed in the pipeline industry possess a high insulating value, are prone to damage, and will degrade over time, contingent on the following. 7.8.1. Coating type and thickness. 7.8.2. Dimensions and shape of the coating, discontinuities. 7.8.3. Soil resistivity. 7.8.4. Duration of exposure. These all influence whether the amount of CP current density at a metallic surface, when subjected to an electrolyte, reaches an acceptable degree of cathodic polarization. Pipe coating conductance has been demonstrated to be linked to the coating percentage bare. An illustration for new FBE-coated piping adjusted to 1000 OCM soil is displayed in Figure 3. Typical conductance versus bare area ratio may differ based on coating type. Note, coating conductance tests were executed as outlined in NACE TM0102 across a broad spectrum of bare areas in low, native, and high soil resistivities. In each instance, there was a linear log-log correlation between coating conductance and percentage bare. 7.9 Design Drawings and Specifications. 7.9.1 Design drawings shall be generated to indicate the overall arrangement of the piping to be safeguarded and the placement of corrosion control test stations, electrical bonds, electrical isolation devices, and neighboring underground or submerged metallic structures. 7.9.2 Design drawings should incorporate an electrical schematic to distinctly identify cable termination points, labeling data, and color for test station and bond box facilities. 7.9.3 Layout drawings shall be produced for each impressed current CP installation, illustrating the specifics and location of the CP system components in relation to the protected structures and to major physical landmarks. These drawings should encompass right-of-way information. 7.9.4 The positions of galvanic anode installations should be documented on drawings or in tabular format, with suitable annotations on anode type, weight, spacing, depth, and backfill. 7.9.5 Specifications should be formulated for all materials and installation methods that are to be integrated into the construction of the CP system.